Welcome to my talk on learned embeddings for geometric data. My name is Isaak Lim. I'm a researcher at the Visual Computing Institute in Aachen under the supervision of Professor Leif Kobbelt, and it is my pleasure to give this talk now. So let's consider this 3D shape shown on the left here. Now, if we want to analyze this shape, then this requires us to extract information about this shape in order to solve a certain task. For example, this could be a classification task shown here. So what we would like to have is some sort of machinery that takes as input such a shape and then is able to output a categorical distribution. And how we can implement this is by mapping our input via this blue mapping function, which we call an embedding, to some output. And this output can be thought of as a vector, and we call this vector an encoding of the input. And then this encoding can be fed into some further, possibly simple function shown in white here, which then produces this categorical distribution. So what we would like to have is an encoding that is a compressed representation of the input that at the same time encodes all the necessary information that we need for the task. And one way of doing this is to construct such a mapping function by hand, but then of course the difficulty is that we might not know how and which properties that we measure, especially local geometric properties that we measure, how we should combine them in order for us to be able to produce such a distribution. And in fact, local geometric alone might not, geometric information alone might not suffice. So we have to somehow extract richer information. So the way we can implement a map that does this is by making use of a neural network. And the nice thing there is that based on the optimization of the parameters of this network, based on the objective or loss function, so that is purely task dependent, it will extract the information that it needs into this encoding vector in order to be able to solve this task. And of course, we're not restricted to classification tasks. This could also be a regression task. And in fact, we can even relate multiple shapes by computing their encodings and comparing them, and then outputting a scalar value that perhaps correlates to a more high-level notion of similarity, for example, perceived stylistic similarity between the two shapes. Another possible application is to compute maps between two shapes in order for us to be able to compute correspondences, which can be challenging based on just computing local geometric properties. We can even extend this approach to inputs that are not necessarily concrete 3D shapes, but something like an abstract notion of a chair. And then the encoding that is computed based on that is able to be used in order to generate a relatively complex 3D geometry again. Now, in order to implement this machinery with this wide field of applications that it can be used in, we have to answer two questions. First question is, how can we actually compute the encodings of geometric data? Meaning, how do we have to construct our mapping function? How do we have to model the neural network such that it can take geometric data as input and is able to produce an encoding? And the second question that we have to answer is that how can we design this embedding space in which the encodings live such that we are able to produce good results? Now let's first tackle the question about how can we represent geometric data as input for neural networks. And it is important to note here that if we compare geometric data to the domain of images, then with images we have a much more benign representation. Namely, here we have a regular grid in which we can order our neighborhoods. And this allows us to extract patterns in our data, and then we can use these patterns on unseen data and are able to generalize. However, if we consider a typical choice of representation for geometric data, namely a polygonal mesh, then we can see that our neighborhood is highly irregular. And then it becomes much more of a challenge for us in order to be able to extract these consistent patterns such that they do not overfit on the specific irregularity of each individual shape. So many representations for geometric data have been proposed in the past. And here I show a fairly exhaustive list on the left-hand side. And over the course of this talk, I will quickly introduce each of these representations and discuss their benefits and possible disadvantages. So fairly early on, people have used handcrafted descriptors because one can typically stack them in terms of a vector, and then we do not have to worry about the concrete irregularity of the neighborhood of the polygonal meshes that were used in order to compute these descriptors. And once we have such a feature descriptor as input, then we can simply feed it into a multi-layer perceptron, which then produces an encoding, which then can be processed further on depending on the task we're trying to solve. Alternatively, we can even take our stacked feature vector and then reshape it into a matrix. And now that we have a 2D domain, we can apply a 2D convolutional network to it in order to compute our encoding. And the benefit here is that we are able to introduce domain knowledge by constructing descriptors. So if we know that certain properties are of interest for a certain task we're trying to solve, then by constructing appropriate descriptors, we are possibly able to generalize well without having a large amount of training data, simply by introducing this prior in form of the descriptors we compute as input into our optimization loop. And this is still of interest because while 3D data sets have been growing, they're still comparably small when compared to, for example, image data sets. The downside is, of course, that we are limited by the expressiveness of the descriptors. So meaning if certain properties are key for a certain task and we are unable to describe them with our descriptors sufficiently, then our performance might suffer. So in order to move away from these handcrafted descriptors, while still being able to handle the irregular nature of the neighborhood on polygonal meshes, people have proposed to simply render images of 3D shapes. So here we place a set of virtual cameras around this 3D object, and then from each camera we render an image of this shape, which is shown here. And then for each image, we can simply process that with a 2D convolutional network. And then according to our set of virtual cameras, so whether they are ordered in some manner or unordered, we can apply a view pooling operation and then process that output further on in order to compute an encoding and then produce, for example, in this case, a classification result. And the nice thing here is that we have not pre-computed any feature descriptors on the shape. These are simple images that were taken of the shape. And here the advantage is that we can indeed make use of prior work on 2D CNNs. And in fact, we can make use of convolutional networks that were trained on other tasks, such as real-world image classification, and then fine-tune them on our task that deals with geometric data. And in fact, we can, depending on the task, extend our geometric data sets by real-world photos in order for us to generalize better. Now, the downside here is that view selection is challenging. So for complex shapes, how do we choose the correct set and position of virtual cameras in order to capture all the necessary information? And finally, if we do a convolution on such a projection of the 3D shape, then we are not really considering the geodesic neighborhood of the shape. So depending on our task, this might be of interest. So to illustrate this, let's consider this neighborhood of this pixel here. And as you can see, each different neighbor, so as we move from one neighbor to the next, we have depth discontinuities. So here we are convolving over the projection of this shape, but in fact, for a certain task, it might be beneficial to consider the actual geodesic neighborhood, which means the neighborhood on the surface of this shape. One approach to deal with this problem of not really working on the neighborhood that is given by the shape itself are approaches that work in the 2D parameterization domain. And what is done here is that we can cut open an input shape and then unfold it into a 2D rectangle here. And by tiling these 2D quads, we have a 2D domain in which we can apply a 2D convolutional network. So by sliding a convolution filter in this 2D domain, we are essentially sliding a convolution filter over the surface of this shape. So this is nice because now we can apply 2D convolutional networks directly to the surface, and we are considering the neighborhood on the surface and not on the projection of a shape. However, depending on the parameterization function that we use in order to map to this 2D domain, we might not have geodesic disks as neighborhood. Further on, we have quite strict requirements in terms of the input data sets. So typically these methods require that the input shapes have genus 0, meaning they have no handles. And of course, this greatly restricts the amount of shapes and data sets that can be considered. And furthermore, they have certain other input requirements in terms of the polygonal mesh quality, such that they can actually compute these unfoldings or parameterizations into the 2D domain. And since the shapes have to be cut open, they're also sensitive to the chosen cut graph vertices. However, this effect can be mitigated by choosing many different randomly during the training process, and then typically these networks are somewhat robust to that choice. A straightforward extension of 2D convolutional networks as applied to images or the 2D parameterization domain are voxel grids. So here we can almost directly apply a 2D convolution to 3D, where then we have a 3D convolution, we have a 2D pooling step, and in 3D we have a 3D pooling step. So all of these operations are straightforward to be extended to 3D. And one such approach is shown on the right-hand side here, where we convert a point cloud here into this occupancy grid, and then we can directly apply 3D convolution and pooling steps in order to compute an encoding, which is then used for a classification task. Now, the downside here is that, of course, that with increasing resolution, we have a cubic growth in the memory requirements. People have proposed ways of working around that, mainly by implementing custom operations. For example, here, instead of applying dense convolutional filters to sparse inputs, as is often given by a voxelization of a surface, which then produces these dense feature maps, we can implement a sparse version of a convolution kernel that is only active on the sparse input signal, and thus is able to preserve the sparsity of the input, which leads to less memory requirements. Another approach is to use spatial hierarchies, for example, an octree here, and then we can define convolution operations at each octree level and then use that in order to do a memory efficient implement a memory-efficient convolutional network on relatively high-resolution data. So the benefit, again, is that we are able to extend 2D CNNs to 3D CNNs in a straightforward manner. We can assume a grid structure and a Euclidean domain, which makes many things easier. However, we might have aliasing artifacts due to poor grid alignment. And if we want to have memory efficiency, then this typically requires us to implement custom operations, which might not be easy to do. A very popular choice at the moment in order to represent geometric data as input for neural networks are point clouds. And this is because, well, on the one hand side, if we consider 3D scanners, they directly produce point clouds. And on the other hand, we have fairly low input requirements if we consider point cloud samplings of 3D shapes. So unlike, for example, the parameterization domain approaches, we do not care too much about the quality of the input shapes as long as we can represent them well by a point cloud. We forgo any connectivity information at all. Now, the difficulty is, of course, that point clouds are unordered sets. And as I've mentioned in the very beginning, we want to be able to extract patterns that generalize well to unseen data. So in order to ensure that we are permutation invariant, two approaches have been proposed in the past in parallel, but they follow the same idea. Namely, they apply the same function, in this case a multi-layer perceptron, to each point in the point cloud set. And what they do then in order to aggregate the information globally is that they apply a symmetric function, so for example a maximum or mean function, to all of the point encodings that have been computed before. And once they have this global aggregation, this can be used as an encoding for certain other tasks. Now, the downside here is, of course, that by using this single global information aggregation step at the very end, we might be losing a lot of information. And this is where PointNet++ comes in, which has been proposed as an extension. So here the idea is that we again have a point cloud as an input, and then we compute a neighborhood graph. And then for each local neighborhood, we use a PointNet to aggregate information locally, which then produces a sparser point cloud. And then we can repeat this process as many times as we like in order to create an encoding which captures information at various scales. Another approach that has been applied to point cloud learning is to define a convolution kernel that works on point clouds. And this is really not straightforward to do because typically we have a fixed number of weights for a convolution kernel that we want to learn. And obviously, the point cloud does not have a fixed size regular neighborhood. So the way this is implemented is by actually fixing a set of kernel points here, shown in black. And then for each kernel point, we compute the kernel response at that kernel point by interpolating the features of the input points within a certain neighborhood based on the distance to that particular kernel point. So here, this is shown on the bottom, where this weighting or interpolation function is shown, is called h here, and the thickness of the arrows indicate how high this point feature here is weighted. And then by summing all of these point features up based on their weights at a particular kernel point, we can then compute the kernel responses. And then here what we do is we do not just sum up the point features based on our interpolation weights, but we also map them to another dimensionality, and then we sum up our kernel responses in order to compute our final output feature, which is the result of a convolution, because a convolution is just a weighted sum. So by making use of these kernel weights, we are able to handle irregular neighborhoods in point clouds. And of course, these kernel point positions do not have to be fixed. During training, we can optimize the shifting of these points according to some objective function. And in this way, we can tune our kernel point positions to our data set, which can improve results. A different approach to implementing convolutions on point clouds is to actually take these sparse and possibly differently sampled points as input and extend them to a continuous function in 3D. And then we can define a convolution operation in this in the continuous 3D volume, and then map the results back to this sparse input that we have. And as I've mentioned before, the benefits here is that if we take point clouds as inputs, we are fairly robust to any type of data that we might have in our data set. However, even if we have existing connectivity information, we completely ignore it. And furthermore, point clouds can be a fairly inefficient representation of 3D shapes. So if we consider planar regions, for example, then we typically have to sample them fairly densely, while if we compare that to a polygonal representation, then we can represent that much more efficiently. Graphs for geometric data have been also proposed to be used as input representations, and these differ somewhat from the graphs that are, or the abstract graphs that are considered in other tasks, for example, in order to analyze social networks, because here we actually have a relation to a three-dimensional surface. And one approach is a spectral approach, where we compute the eigenfunctions of the normalized graph Laplacian of a neighborhood graph computed on this point cloud here. Here we see some eigenfunctions, and then in this spectral domain we can compute a convolution and then map the result back to the vertices. Another approach is to make use of graph convolutions, and here we have to consider the following problem, namely that for each center vertex here we might have a different number of neighbors, and even if we had the same number of neighbors in a graph, we do not necessarily have any way of ordering them. So the way of working around this irregularity is actually similar to what has been proposed in PointNet and other methods, namely that we treat each neighbor the same. So we apply the same function to each neighbor of the center vertex, and then we aggregate that information by applying a symmetric function in order to compute a result for this green vertex here. The benefit again is that we're also fairly flexible in terms of the input quality. We can use these types of representations on point clouds and on meshes. And here, in fact, we do not care too much about the quality of the meshes. They can be non-manifold, and these types of approaches on graphs also work on them. However, the downside here is that even if we have high-quality meshes, even if we have manifold meshes, then each neighbor is treated in the same manner. So, for example, if we consider this patch of a manifold mesh here, then we have some way of ordering our neighbors, and this is completely ignored because we treat each neighbor the same and then aggregate the information by a symmetric function. This is where approaches that work on curved surface patches come into play. So one approach is shown on the top here, where we extract geodesic disks of our 3D shapes, and then we have to deal with an irregular neighborhood due to the mesh that lies underneath this geodesic disk. And the way we deal with this is in a very similar way in how we deal with irregularity in the neighborhood for point cloud convolutions, namely that we define the weighting functions for each kernel position on this geodesic patch, and then we can apply such circular geodesic disk-like filters, and we only have to choose a certain orientation for them or pool over all possible orientations. Of course, we do not have to fix such a weighting function, but this can also be learned. by, for example, making use of a Gaussian mixture model that is optimized jointly with the weights of the kernel. So the nice thing about these approaches is that we are able to respect the geodesic neighborhood, and we have to throw away less information as with the approaches that work on graphs. However, in contrast to them, we do have some input requirements. And furthermore, the orientation of these filters is not always straightforward to fix. Now I will present our contributions that we have done, and the first contribution is how we can extend these approaches that work on curved surface patches. And as mentioned before, these approaches typically rely on a kernel-based resampling of such an input mesh patch, so meaning for each kernel position here, I somehow have to interpolate the input features. And this can lead to a loss of data fidelity, and depending on the information that is stored at each mesh vertex, the interpolation operation is unclear whether it's meaningful. And furthermore, depending on the choice of these geodesic convolutional filters, we can have heavy preprocessing costs. So what we propose to do instead is that we enumerate our neighborhood in a consistent manner. And we can do this by considering the center vertex C and then fixing a starting position in our neighborhood. So here in this case, we will start at the vertex 1 here and then construct such a spiral. And we can keep on doing this in this clockwise manner. And in this way, we have enumerated our neighborhood in an ordered and consistent manner. And now that we have such a sequence, we can construct a feature sequence simply by making use of the feature information stored at each mesh vertex in that sequence. And since we have an ordered sequence now, we can compute many different encodings of that local neighborhood information. For example, we can make use of a LSTM, so a recurrent network that works on this sequence, and this allows us to consider sequences of varying length. If we fix the length of our sequence, since it is ordered, we can simply stack the feature vectors and then use a fully connected layer in order to compute encoding of that local neighborhood. And as has been done later on, we can also simply define weights for each position in our fixed length ordered sequence and then directly compute a weighted sum, which is a convolution operation. We have compared this result to previous work, namely geodesic convolutional networks, and here we show the architecture. So in this task, we want to compute correspondences of such an input patch to a vertex on a reference mesh. And shown in red here are the 3 geodesic convolutional filters. And in order to compare them, to compare our approach to the geodesic convolutional networks, we simply replace these convolutional filters with operations. Shown here is the recurrent network that works on our spiral operator, which is shown here, which produces this ordered sequence of neighboring vertices. Alternatively, we also consider the case where we use fully connected layers to encode the features sequence. Here you see some results. So on the x-axis, we have the geodesic neighborhood, and on the y-axis, you have the percentage of correct correspondences that were found within a certain geodesic radius. And as you can see here, even for fairly small geodesic radiuses, we are able to produce a high number of correct correspondences. And of course, as we increase the geodesic radius, this percentage rises. Here shown below are the other approaches that work on curved surfaces that have been proposed in the past. As I mentioned before, we have to pick a starting position for our spiral. So this means we are not rotation invariant. And what we show here on a different data set is the result of our networks if we randomly rotate these spirals. And as you can see, we produce fairly robust results. So here we have 100 such random rotations applied, and we produce results that are indistinguishable from each other. And this is because during training, we learn to be robust against these rotations by rotating the spiral randomly. So far, we have considered individual representations for geometric data, and each of these representations have certain advantages and disadvantages. And what we will now show is the benefit of combining these representations. And the idea here is that by combining representations, we can mitigate the disadvantages that each of the representations might have individually. And we showed this in a task, in an outer encoding task, and this is shown here. So on the left-hand side, we have some input shape, and then we have an encoder that produces an encoding Z, and then this encoding Z is fed into a decoder, which again produces a voxelized representation, which should be a close approximation of the input. And the benefit of using a voxel representation here is twofold. First, the encoder and the decoder are straightforward to implement. We can directly use 3D convolutional networks on both ends. And the second reason is that we are able to capture the global structure of the shape fairly well. However, we are limited by a low resolution due to memory requirements. On the other hand, if we consider point clouds as a representation for both the input and the output, our representations are highly unstructured. However, the benefit here is that we are able to capture fine details of the shapes. And now we propose to combine these two representations in order to benefit from advantages that both of them give us. Namely, we want to combine the structure that is given by the voxel-based approach with the ability to capture fine details with fewer memory requirements as given by the point clouds. So here we show the encoder we use, and here you can actually already see a direct application of this hybrid representation we opt for. Namely, we embed our input point cloud into a 3D grid, and then for each local cell in this 3D grid, we encode the local point cloud patch within its vicinity via a PointNet. And in this manner, we are able to compute an encoding vector for each cell, which is represented on the right-hand side here. And while we have a low resolution 3D grid, this is actually a much more expressive representation than a pure binary voxel grid, such as an occupancy grid, for example. Because even though we have low resolution, each cell captures possibly complex local point cloud patches. And by making use of this rich information in this relatively low resolution grid, we can then directly apply a 3D convolutional network to compute a good encoding of the input set here. And now that we know how our encoder is constructed, we have to consider how we can actually generate point clouds. And an obvious way of doing this would be to use a multi-layer perceptron, but the downside here is that then we have a fixed number of output points, and furthermore we apply an arbitrary ordering to the output points due to the fixed nature of the multi-layer perceptron. What we opt for instead is to stick with our hybrid approach. Namely, we use our encoding Z and then have a 3D convolutional network that outputs such a 3D grid. And with this 3D grid, we should be able to capture the global structure of the shape well. And now what is left to do is to produce point clouds such that we are able to capture the fine details of the shape. And to this end, we follow a similar approach to one that has been introduced before here with AtlasNet. Namely, we have some encoding Z of an input, and then we have a sampling of a 2D domain, and together, by combining these two inputs into an MLP, we map to a 3D position. They do this in a global manner, while we want to learn these types of maps locally for each cell that should contain a local point cloud patch. So this is shown here, where we have an encoding for each cell, and then we sample a 2D domain a number of times, combine this information, feed it into an MLP, and this produces 3D offset vectors from the cell centers. Now what is left to do is to determine which of these cells are actually filled, and if they are filled, then how many points these cells should produce. We do this by feeding the encoding at a certain cell into an MLP, and this produces first the probability whether the cell is filled or not, and then a density value delta, which tells us how many of the total number of points that we want to output should be generated by this cell. And by combining this information, we can compute an integer m, which again then tells us how many times we actually have to sample this 2D domain, or if we have to sample that domain at all. Now, this means we are variable in the number of output points. Here we are shown a test input and a test output of the same size. However, we can increase the number of points that we generate, and as you can see here, we still nicely approximate the underlying continuous surface. On the other hand, because of our hybrid representation with a fairly low number of points, we're still able to capture the global structure of the input shape. We are also variable in the number of input points, so here you can see a very extreme case of upsampling, whereas input on test set examples, we just have 50 points in our point cloud, and then are able to approximate the ground truth fairly well with just 50 input points. Indeed, we are not restricted to geometric data in terms of point clouds as the input. We can exchange that with encodings of images, for example, for the single view reconstruction task. And we are even able to produce, train a variational autoencoder, which allows us to sample Z from a Gaussian distribution in order to generate these shapes. And we compare our approach to previous approaches on a data set. And as you can see here, we are able to outperform them in terms of the chamfer distance to the ground truth. Here you can see some qualitative examples, and I want to point out to you again that due to our hybrid representation, both of the input and the output, we are able to capture the global structure of the shape well, while also preserving the finer details, where other competing methods can struggle in certain cases. Now that we know how we can compute encodings of geometric data, either by individual representations or by combining different representations, we want to now discuss an approach on how we can design the embedding space. And for this, I want to refer back to the very beginning, where I briefly mentioned that given two shapes, we might want to be able to output whether these two shapes are stylistically similar or not. And this is a challenging task because it's quite difficult to write down what this vague notion of stylistic similarity actually means in terms of a mathematical model. And we propose to solve this by making use of metric learning. And the way we do this is by having these 3D input shapes, and here we choose as representation for our networks, shown as these blue boxes here, images, rendered images. So here in red, we see the chosen view that we have selected in order to represent this 3D shape. And by making use of this representation, we are able to quite easily extend our data set to make use of real-world photos. And now we use our neural networks to compute encodings of these inputs, and then we want our embedding space to be such that encodings of stylistically similar shapes are placed close together, while stylistically dissimilar shapes should be placed further apart. And we implement this by making use of a triplet network architecture. So our training data consists of triplets where we have a reference input, a so-called positive input, which indicates that these two inputs are stylistically similar, and a negative input, which is stylistically dissimilar from the reference input. We compute an encoding of each of these inputs by using the same neural network, and then compute the distance in this embedding space between the encodings. So one distance, what we call d plus here, which is the distance between the reference input and the stylistically similar input, and d minus, which is the distance of the reference input and the stylistically dissimilar input. And obviously, what we would like is that d plus should be small and d minus should be large. And we optimize this objective by formulating it as in terms of hinge loss. So here we have a scalar margin m. And what this loss does is that if the distances are closer to each other than a certain margin, then the encoding of the stylistically similar input is pulled closer to the reference input, and the dissimilar input is pushed further away. And once these encodings are far enough apart, meaning that they satisfy this margin, we do not have any gradients that act on them, so we do not have any pushing or pulling of these encodings any longer. Here we show some results. So on the left-hand side, you can see an approach that worked by making use of handcrafted descriptors and then tuning the weights according to a training set in order to combine these different descriptors together in order to classify the stylistic similarity or dissimilarity for these triplets. And on the right-hand side, you see our results. So first we trained on just 50% of the geometric training data, and as expected, we performed worse. However, by just adding a small number of photos to our reduced training data, we are able to achieve competitive results in the style classification accuracy. And if we use 100% of our training data, of course, because we are able to extract relevant information automatically instead of relying on the expressiveness of pre-computed descriptors, we are able to outperform state-of-the-art. And we can even further improve these results by making use of real-world photos. And with this, I come to the end of my talk. So we have first discussed encodings of geometric data by looking at different individual encodings, individual representations, and how they can be encoded with advantages as disadvantages. And we've shown an extension that works well on curved surface patches. And we have noted that if we are able to actually combine representations, then we can benefit from advantages that both representations have, while mitigating the disadvantages that they each have individually. And then we've discussed a way of designing the embedding space that goes beyond categorical cross-entropy laws that can be applied with the approach of using metric learning on problems such as learning stylistic similarities. And finally, as an outlook, we believe that finding more meaningful combinations of representations for different tasks can be highly beneficial in the future, and this is something that we should investigate. thank you for your attention. Yeah, it was a pleasure to give this talk.